Okay, section 14.2 is about Euler. Euler's a mathematician, right? We've encountered him before. Section 14.3 is about Hamilton, another mathematician. And he's done a lot with geometry, which kind of makes sense. Euler also did a lot with geometry. And so we're going to look at something called a Hamilton circuit as opposed to an Euler circuit. So a Hamilton circuit is a circuit that visits each vertex exactly once, returning to the vertex, to the starting vertex to complete the circuit. That should have a parenthesis at the end. I don't know why that's not there. So with Hamilton's circuits, we're not concerned with crossing every sidewalk. We're just concerned with going to every building, right? So it's kind of like if you're running errands, you have a list of places you need to go. You might be wanting to worry about how efficient you are, but you're wanting to make sure you cross every location off the list. You don't need to go on every street that connects the buildings together. That's Hamilton circuit. Okay, ready to see one? Everybody have it written down? We're good? That one was a shorter one. All right, so we've got a graph, and we have a list of things right below. We've seen this happen before. It happened in our last section, and we're going to try and decide if we have a Hamilton circuit. If it fails, we're going to tell why it fails. Okay? So this is going through these different points. I'm going to try and draw them in colors and then change my color, or at least erase the color I just did to see if it'll work. So this one says I go from A to E, E to C, C to D, D to E, E to B, and B back to A. Okay, so, yes, Kyle.
Couldn't you just look, make the first and last one the same, and then see if in the middle they're not repeated?
That's part of it, but there's actually another caveat that you have to be careful of. So did everybody hear what Kyle suggested as a sort of thing to check? Because he's right. We want to make sure we start and end at the same point, which this one does. And we also want to make sure that we don't hit hit a point more than once. I think that's the other condition you said. There's another condition that we could possibly end up doing besides that. There's one more thing we'd have to check besides those two conditions. We need to make sure we don't miss anything. Right? The conditions you gave did not preclude the possibility of skipping one of them. You know, we just didn't go to Walmart when we really need to go to Walmart today. Right? You skip it, and that's a problem. So yes, we could do that. This one does fail. On what count? Why did it fail? Yeah, it went to E twice. So this is not Hamilton. Because it visits E, I think it was E, right? Yeah, twice. And I've made a mess of things. All right. I didn't even make my yellow lines very well. Okay, to start like that. Am I missing anything? Yep, BC's missing. All right, everything else is still there. It's a little wonky looking now, but it's still there. Okay, so let's give Kyle's options a try and see if we can see if they fail without actually tracing it, and then we'll trace it to make sure that it actually worked. So does it start and end at the same point for part B? Yes. Does it list any vertex except for the A's, starting and the ending, more than once? Nope, no repeats. Does it list every vertex? Yes? So our expectation, based on those three things that we just checked, is that it is a Hamilton start, right? That is a Hamilton circuit. And let's trace it to make sure it really worked. So it goes from, I've left off one of my lines. Y'all didn't tell me I missed that one. There was missing. That matters. That's actually something else I meant to say. We have to make sure there's actually an edge connecting things. For example, if I had one that said A to D, that would be a problem. It might actually meet all the three criteria we mentioned, but there might not be an edge connecting them, so that's another thing too. All right, so let's go A to E, E to C, C to D, D to B, and B to A. And did it work? It did. We didn't visit any vertex twice. We visited all of them exactly once. We didn't cross anything. We didn't go off the path. Those kind of things, those off the edges. All right, how about this one? No. Why not, Jasmine?
It doesn't end in the correct spot and it skips C.
Awesome. So this one fails a couple of times. So this is a no. Well, let's get the color back. No, or not Hamilton. Because it starts, ends at different points. So at different vertices. And it skips what?
C.
We do not manage to get to C. Okay. I think that's the only things that happen on that one. Does that work? Those are the reasons it fails. Okay. So we talked about a type of graph, I think it was in section 14.1, called a complete graph. Complete graphs means that every pair of points is connected with an edge, or every pair of vertices is connected with an edge. That's a complete graph. Now, if you have a complete graph, then, with 3 or more vertices, then you will have a Hamilton circuit. If it's complete, it has a Hamilton circuit. And it kind of makes sense that that would be reasonable. You've got lots of edges. So getting in and out of lots of the edges, going lots of different places seems like a good thing if you're trying to find one of these circuits. And the second thing on this slide talks about when the Hamilton circuits are considered to be the same. Hamilton circuits that differ only by their starting point will be considered to be the same circuit. So let's take a look actually back at the one that we had a Hamilton circuit on which was B above here, or before over here. What this statement is telling us is that this list is all well and good, but it could have started at, say, C, and I could have gone through and gone from C to D, D to B, B to A to E, E to C. And if I went through that list of points, it would be considered the same circuit, because I'm following the same order. So there used to be these things that happened. I never participated in one, but I know my parents did when I was younger. And they were called progressive dinners. Have you ever heard of a progressive dinner? Okay, I've got a few nods of heads. If you haven't, it's fine. But what progressive dinners did is that you would have a few host locations. So think about it like people's homes. And you would have a bunch of people who were moving through the homes, and they were having different courses of food at different places. So you'd go to this location for your salad, and you'd go to this next location for your entree, and this next location for dessert, and the final location for your coffee or something like that. So that's fine if you started with your salad and you moved forward, but there were some people who started with the main entree, and then they went to their coffee, and then they came back to their salad, and they ended with, like this. They go in a different order, okay? That's a progressive dinner. It's the same thing as this. Right? You're just trying to make them all go to the same locations in the same order, but we don't really care where they start. That's what a equivalent Hamilton circuit is. So we're going to decide, this is our picture. Does it match yours? Let's make sure. We're just going to start with that question on my graphs. I believe it does. Yes? Does it look like it has all the pieces yours does? Fantastic. This says to determine whether the graph has a Hamilton circuit, and if so, you want to find one, and if it has one, there's lots of answers. Now, a real quick way to decide if it has a Hamilton circuit is if it's complete. Now, if it's not complete, it doesn't mean it doesn't have one. It just means you're not guaranteed to have one. So the first thing you should check when you're looking at it is it a complete graph? It's not. Why does it fail to be complete? Yeah, that bottom line from U to V is not there, right? So this is not a complete graph. So we're not guaranteed that this has a Hamilton circuit. But that doesn't mean that it doesn't. So what we do is we attempt to find one. That's legit what we do. So we need to start somewhere. Just because it's at the top, I'm going to suggest that we start at X. So let's try and start with X and see what happens if I go through, sorry, let me put that there, let me put it here. Where could I go after X? U. Okay, so we're going to go X down to U. T, okay, U up to T. T to W, okay, T to W. W to V, and then V back to X. Okay, so let's make sure it fit our criteria. Did it start and end in the same place? Yes. Did it hit every vertex? Yes. Did it do any vertex twice? No. And did we go off of any of our edges? No, we didn't. So, yes, this one has a Hamilton circuit, and this is one of them. It's certainly not the only one. It's not a unique statement, but this would be a Hamilton circuit. All right, so I gave an example, the progressive dinner, which is an application of a Hamilton circuit. There's going to be some other ones where they're going to give you an application, and you're going to try to decide whether it's representing an Euler circuit, which means you cross every edge once, or whether it's a Hamilton circuit, which means you hit every vertex once. Okay? So this one says the vertices of the graph represent the places where the paths in a botanical garden cross. Okay, so the sidewalks in a botanical garden, every time the sidewalks cross, that's a vertex. And the edges represent the actual sidewalks, the paths between those two locations. A visitor wants to walk along each path exactly once and return to his starting point. Is he attempting a Hamilton circuit, or is he attempting an Euler circuit? Euler. How do you know? Because it says paths. Okay, Euler circuit is all about the paths. He wants to cross each path exactly once. So this is an Euler circuit he's trying to complete. Now, that may or may not make sense. In a botanical garden, it might, because along the sidewalks, there's going to be different, plant life and so forth that you might be interested in seeing along the way. But like, imagine that you were at a zoo. You might not be interested in the plant life that along the way. You might only be interested in seeing the monkeys and the tigers and the giraffes, right? You're only interested in going to the specific locations, not crossing all the paths to get there. So it depends on the context, which will depend on which one you have. All right, so we've said that there's lots of Hamilton circuits in a graph. If you have a complete graph, we know exactly how many Hamilton circuits there are, and you've seen this notation before. If you have n vertices, then there are n minus 1 Hamilton circuits, specifically in a complete graph. Not just any graph, but a complete one. Okay, so real quick reminder. That factorial notation, what does it mean? Yep. Several of you are saying it. That's good. 4 times 3 times 2 times 1. What would that be? That's 24. So if we're doing an example of the actual problem, determine how many Hamilton circuits there are in a complete graph with 10 vertices, what would that be? 9 factorial, which is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. I do not have that written out, so somebody is going to have to tell me what that multiplies to. Anybody know? Emma, are you getting it? Trying? Okay.
362,800.
Okay, so when they told you that there were many answers, you didn't probably expect 300,000 answers, right? But there's 300,000 answers, so it's quite a lot. That's the number of Hamilton circuits in a complete graph. Okay, we're going to talk about a weighted graph. A weighted graph is something that your phone uses all the time. So let's talk about what a weighted graph is. This is a graph with a numerical value associated with each edge. And a minimum Hamilton circuit is the one that has the least possible weight. Okay, so I'd like to tell you what I meant, or ask you what you think I meant, by the fact that your phone does this all the time. Does anyone use your phone, some kind of a map in your phone to get places? We probably all do. I do too. Sometimes even places I've been before because I'm still afraid that I'm going to end up in the wrong spot. Okay? Your phone gives you options on how to get somewhere, correct? And it takes lots of things into consideration. What is one of the things that it does when it tries to get you there as it's considered its best option? Traffic, right? And so what it's trying to minimize if you're doing traffic is what variable? What are you really trying to minimize?
The amount of time it takes to get there.
The amount of time. So one of the things your phone's trying to do is get you there in the shortest amount of time. That's one of the options. What are some of the other options it does? So the time would be the weights, by the way. The length of time for each of the segments would be the weights. It might be tolls. So it might be looking at getting you there in the cheapest way possible, right? In terms of cost of the roads. Yep, that's one of them. There's one other one that it might be doing. It might be doing the actual mileage, right? Driving the fewest number of miles from one place to the next. In that case, it's probably trying to conserve your cost of your gas. So the weights are not necessarily what you always think they are. They may be some other variable that you're trying to minimize. Now, the ones we're going to work with are just going to have numerical values assigned to them, representing some kind of a quantity. They're not going to be defined for us. But our goal is going to be to try to find a Hamilton circuit of minimum weight. There's one algorithm, and this is a messy one, but it's called the brute force algorithm. The brute force algorithm says that you're going to choose a starting point, and you're going to list all Hamilton circuits with that starting point. And then you're going to find the total weight of every single circuit, and then you're going to pick which one's the smallest. Okay, The map app in your phone clearly has the capability to do something like this, right? I mean, computers can do things very quickly, much more quickly than we can. A lot of things that are sometimes tedious for us are really quick on a computer. But even your computer, the app in your phone, right, it doesn't always do this. Let me talk about what I mean by that. Have you ever looked at the map and you're like, but I really don't want to go on that road? And you click somewhere else, and maybe even the time went down on the option that you picked. Have you seen that happen before? Yeah, right. So your phone's also somehow taking into consideration sort of the most reasonable thing that it thinks that you would want it to do. Maybe based on the patterns of what you've done before or the patterns of what most people do, right? So it's not actually doing a brute force algorithm. We're going to see why we don't want to do it in our next example. But this gives you all possible options. Okay, so let's take a look. This is our picture, and it is a complete graph now. It's almost the same graph we had before, but notice it actually has the DE line at the bottom, whereas we didn't have that line at the bottom before, right? So this one's actually complete. So we need to pick a starting point. That's the one unique thing that we're going to do. It tells us very specifically, do that, and then everything else is going to be all the options after that. So we need to pick a starting point. I'm going to pick just the top point, G, like I did before, okay? But this is just arbitrary, that part of it. So we have options, and because it's a complete graph, we're going to have lots of them. In fact, how many points vertices are on this graph? 5. So how many circuits are there?
24.
There are 24 circuits. So we are going to write down 24 circuits. We are not going to find the summation along all 24 of them. Okay? I don't think that's really in our best interest of time. But we're going to write them all down. So I could take G, and I could just go all the way around this puppy, right? So that's what I'm going to start with. So G, F, E, D, C. And then back to G. It always starts and ends at G. And now I'm going to try to minimize my changes along the way so that I get all the options. So I'm going to follow most of the same things I did before. G, F, E, D, C, G. I'm going to do G, F, E, D. G, F, E, sorry. So G, F, E. If I go to D, then I have to go to C and back. So I can't go to D. I have to go E up to C, D, G. So I'm going to switch the C and the D now. So C, D, G. I just switched those two. But maybe I don't go from G to F to E. Or do I do G, F, and E? But at this point, I'm stuck. I have to either do C or D next, so I don't want to do that one. So I won't do E next. I need to pick a different letter. So what's a different third letter I could choose? C. And then at the end, I could do C, E, F, G. Or I could do C, F, E, G. And those are all my GFCs. So I've done GFE, I've done GFC. I also need to do GF what? D. So GFD. So I could do DCEG, or I could do DECG. We're at 6. Having fun? Not really. Yes.
Doesn't the Hamilton circuit have to hit every single point?
It does.
Why would it go G, F, C, E, F, G, and not hit D?
I think D's listed everywhere unless I made a typo, and I may have. I typoed. These were supposed to be D's. I'm sorry.
I was just
Yep, you're fine. They're D's on that one. Yes. Thank you for pointing that out. We got this fixed. Cool. Thanks. Because this is 6 of them. And how many do we say there really are? 24. And we're never changing the G at the beginning and the G at the end. Those are staying put all the time. So let's do just a few more, and then we'll say that's enough. We've got the idea of what we're trying to do here. We've done all the GFs that there are, though. Agreed? There are no other GFs because we've gone GF and we've got the third letter changed every single time. So we need to change now from GF to G something else. So GC. So we could do GC, and then we could do E, D, F, G. Did I get them all? I think so. And we keep the first three the same, G, C, E, and then we switch the F and the D. We keep the first two the same, and we change E to F. I've lost my letters. What letter am I missing at this point? E. Here we go. And we do it again. We do G, C, F, E, D, G. And then we do G, C, D, E, F, G, and G, C, D, F, E, G. This is half of them. Okay, ready? Understand what we're doing. Do you catch what we're trying to do? We're trying to list all the different ways you can do this, and this starts to feel like a permutation, right? And it is, because we already saw that we're getting 4 factorial here. That's permutations that comes from. So we're just going to do a couple of these, and we're going to write out what the circuits are. So let's just do the top one and the bottom one, because they're separated by enough to allow us some space to work. So we're going to figure out what the weight is, of this one. So we're going to list out how, like, the weight along the path. So if I go from G to F, how much is that? 15. And then F to E, 17. E to D, 10. D to C, 12. And then C back to G is 10. Okay? So somebody go ahead and grab a calculator. I do not have this total written down because I didn't write anything in the same order. Does anybody have it? What's that?
61.
Is it 61? I think here he's adding it in his head, so let's double check. Somebody else added for us. 64? Okay, I've got a couple people 64. You're really close. Okay, so this is 64. Our goal is to find the minimum one. So obviously, if I found all 24 of these circuits and I found the summation of all of these things, I'd be able to figure out which one is the minimum one. That's what brute force means. It means we're going to dig it. We're going to do all the hard work that we can, and we're going to give every single possibility, and we're going to pick the smallest one. Okay, that's brute force. Let's do one more of them here at the bottom. So do this one. So you've got GC, which is 10. And then CD, that's 12. DF, that one's 21. And then FE, did I miss one? DF, oh no I didn't, okay, FE, what was it? 17. And EG, 13. Okay, add those up. 73. So that's definitely a less desirable option because it's 9 more than the one before. But this is tedious, right? And even your phone doesn't do this. And you know it doesn't because you've seen it not do this before. So this is what we call inefficient. An efficient algorithm is an algorithm that does not take a computer very much time to do, or you. If something is efficient, it means it's quick to do. Okay? What we just did is not efficient. An approximate algorithm, it doesn't take very long for it to do, and it also gives a reasonably good solution. It may not be the perfect one, it may not be the minimum, but it's pretty close. Right? We're sort of okay enough with it that we're going to go with it anyway. Right? This is like balancing your checkbook. I don't know if you guys do that. I hope you do. And you're off by 2 cents and you can't find it, and you finally decide, I don't care. I'm close enough. Those 2 pennies can just disappear. It doesn't matter. Okay, so it's a close enough idea. Okay, so that's what approximate's going to be. It's going to be close enough. So the algorithm that we're going to use, that's the close enough idea, is called the nearest neighbor algorithm. And we'll do that on the next slide, so I'll pause. Okay, so I want to just visually describe to you what the nearest neighbor algorithm does with our last example, and then we'll write out all the details of how we actually go about doing it. So we're going to start again with point G. The nearest neighbor algorithm says, I'm going to look at the edges all extending from G, and I'm just going to pick whichever one's the smallest, and I'm going to do that one. Okay? So you've got 10, you've got 13, you've got 13, and you've got 15. The smallest one is, I think there was a 10. Wasn't there? 10. So we would do the 10 one. So our first thing we would do is we would go G to C. I'm going to write it down, actually. After C, we can't go back to G, but we want to pick its smallest one. So there's a 12, a 15, and a 15. So which one would we pick? We'd pick the 12. So we'd go to D. Okay, so this was 15. I'm sorry, no, it was 10 rather. 10, and then what was our next one? 12. Okay? After D, we have to either go to F or to E. Which one's smaller? 21 or 10? 10. So we go to E, and it's 10. And then from E, we have to go back to the starting point because we've run out of letters, so to speak, run out of edges or points to hit. And so we're back at G, and that value to go from E to G is 13.
We didn't get F.
Oh, I'm sorry. Go to F first. How about E to F? My bad. E to F, 17, right? Sorry about that, 17. And then F back to G. F to G is 15. So just real quick, what does that add up to? I have no idea if it's a number that's smaller than what we got before, but 10 plus 12 plus 10 plus 17 plus 15. 64. So it's pretty close to the things we were getting before, right? It's as small as the other one that we got anyway. And it's good enough. That's what the nearest neighbor algorithm does. So the nearest neighbor algorithm says to start at one of the points. We'll call it A. Choose the edge or least weight, as I should say of least weight, connected to A. At each vertex, repeat this process, going to all the vertices that we haven't visited until you get back to A. It's what we just did. You start somewhere and you choose the path that's the smallest number, and you keep choosing it until you get back to where you started. That doesn't always work. Sometimes you're forced now to go along a path that's worth 21 back in the other graph, right? But it's a reasonably good estimate that's much more efficient than the brute algorithm. So this is basically what I do when I run errands. And it's probably what you do too, but you didn't realize it. So you think about all the locations where you need to go. And what you tend to do is to take the most direct way there possible, right? So there's lots of ways to get from here to Walmart, but there's lots of ways you're not going to go, okay? So you're trying to minimize your time, which often means minimizing distances, although you might want to avoid the entire, all the lights fiasco on Kickapoo. You may choose to do that too, right? There may be a reason to choose something different. But you're trying to minimize your location or your time or your distances that you're traveling from one location to the next. We do this all the time just by nature. Okay, it's how God designed our brains to think about how to get things done, is to be efficient. So we're going to do this with an example And we're going to start on part A at F and then on part B at G. There's nothing real specific about them. It's just a location to start from so that it's not completely arbitrary. So if we start at F, will we go to I, H, or G? H. Why? That's the lowest one, and it's a 2. I'm going to write down the numbers as we go. After H, I need to either go to I or G because I haven't visited them. Which one will I go to? I. What's its weight? Oh, it's a 4. Okay, after I, I'm out of choices. I have to go now to G. It doesn't matter what's least now because I still have to get to all of my vertices. So what is IG? That's 3. And then G puts us back at, F. And GF is 6. So it's kind of unfortunate that we get the plus 6 at the end. That was a large weighted one, but we're out of options then, right? So we have 2 plus 4 is 6, plus 3 is 9, plus 6 is 15. So this is a weight of 15. We're going to start at G now, and we're going to do the same process. We can start anywhere, so we're just doing a couple of them. So if I start at G, do I want to go to H, I, or F first? I. What is that weight? 3. After I, do I want to go to F or H? H. And what's that weight? 4. After H, I'm out of choices. Where do I have to go? F. HF is 2. And then I go back to G, and FG is 6 again. So 3 plus 4 is 7, plus 2 is 9, plus 6 is 15. It happens to be the same. That doesn't always happen. Okay, there's not a, this is going to always be like a magic number kind of thing. It doesn't do that. But it happened to be the same number.